Yes,
sir. The point is, the timetable is fixed by SSB director, so I cannot change it. Okay,
yes, sir.
I don't have liberty to change it.
Yes,
That's the problem, right? And they have remuneration depending on the time of time a teacher teaches. So
problem is, sir.
Yeah, you please manage yourself.
Yes,
Yeah. So I can't do anything officially.
Thank you,
right?
sir. Thank you, sir.
Yeah. Okay. Well, let me share the whiteboard. Okay. Is my voice audible?
Very clear, sir.
Whiteboard is also visible, right?
Yes, sir.
Okay. Yesterday, there were only 2 students. So I was not in good mood to continue. I took for 1 hour only, I think. Okay. Today, I want to start from where I left yesterday. That is, I'll show you. Yeah, that is page 78. I start from page 78. Okay, right? After corollary 4.3.3. This is after corollary 4.3.3. Right? Yesterday we were discussing that corollary 4.3.3. So after that, I want to continue. Okay. And then there is a theorem 4.3.4 that you can see, right? Just it is application of previous theorems. So I'll come into theory part. Okay. After other theorem 4.3.4. I will start off. Okay, let me discuss that theorem otherwise.
Yes, sir.
After 4.3.3 corollary. This is corollary. Right. I'll discuss theorem 4.3.4. Right. This is application of previous results. A normal linear space is finite dimensional. A normed linear space is finite dimensional. If the closed bounded sets are compact. The closed bounded sets are compact. Okay. Proof is application of previous results. Okay. For example, theorem 4.3.2. Theorem 4.3.2 says that in exam you should not mention by theorem 4.2. By theorem 4.3.2 you get only if part like that. You should not mention. You should write down the statement of this theorem which you are referring. Okay. What does this theorem 4.3.2 say? If every closed bounded subset of X is compact, okay, of a normal linear space of a normal linear space N of a normal linear space N is compact, then N is finite dimensional. Okay, this we proved yesterday. If every closed and bounded set of of a normal linear space N is compact, then N becomes finite dimensional. This we proved yesterday. Okay, so if you assume this part, okay, that is only if part, okay, let the closed bounded sets, closed and bounded sets in N be compact. Okay, Now, for this assumption, you apply this theorem. Okay. If in a normal linear space N, closed and bounded sets are compact, then by this theorem, you have that N is finite dimensional. Okay. Then theorem 4.3.2 implies N is finite dimensional. Okay. So in exam, you have to write down the statement of the theorem. You should not simply mention the number and finish. No, you have to write down when you are referring a theorem or a proposition or a lemma, you should write down the statement completely of the theorem or proposition or lemma respectively. Okay. So if closed and bounded sets are compact, then N becomes finite dimensional. Conversely, if N is finite dimensional, if N is finite dimensional, okay, right, converse part, let N be finite dimensional, okay, then by Heine-Borel theorem, right? See, Heine-Borel theorem says what? A contained in Rn is compact if and only if A is closed and bounded. Okay, this is what the Heine-Borel theorem says. Heine-Borel theorem. Borel is a mathematician. Was a mathematician. Heine-Borel theorem says if A is a subset of Rn, this is compact if and only if A is closed and bounded. Now we are saying N is finite dimensional. So N will be isomorphic. Okay. N will be topologically isomorphic to Rn. Okay. So if you take a closed and bound, so if you take compact sets in Rn, they will behave. Yeah, if your N is finite dimensional, okay, so it will your N will be isomorphic, topologically isomorphic to Rn. Topologically means I will explain. So topologically means there will be a linear map to linear spaces are said to be topologically isomorphic if there exists a linear map which is 1, 1 and on 2, and that T is continuous and T inverse is continuous. That's what we mean by topologically isomorphic. T should be continuous and T inverse also should be continuous. Okay. Then we say N and N dash are topologically isomorphic. Okay. If between two normal linear spaces, if there exists a linear map T such that it is 1, 1 and on 2, such that T is continuous and T inverse is continuous, then we say that N and N dash are topologically isomorphic. Okay. So if your N is finite dimensional, you can show that N is topologically isomorphic to Rn. So in Rn, a compact set is closed and bounded. Therefore, in N also, compact sets will be closed and bounded. Okay. So now these two will be giving together. Right. So if you call this star, so this statement and star, this statement and star, this statement and star imply that that closed and bounded sets, subsets in N are compact. Okay. That's how you can prove this part. You are assuming N is finite dimensional. Then you will be taking closed and bounded sets, and a finite dimensional space N will be behaving as Rn if the space normal linear space N has dimension small n, then it will be behaving as Rn, and in Rn what happened to 2? Okay. In Rn, yeah, I wrote in 3. Okay. In Rn, closed bonded sets are compact. So in N also, closed bonded sets will be compact by Heine-Borel theorem. Okay. That's how a normal linear space is finite dimensional if and only if closed bonded sets are compact. Okay. Now let us come to the concepts of isometrically isomorphic. Isometrically isomorphic. Isomorphism. Okay. This I can move. Right. Okay. Let me explain what we mean by isometrically isomorphism. Okay. Say we have two normal linear spaces. N and N dash are normal linear spaces, or normal linear spaces, or normal vector spaces, Okay. If you have a linear map T from N to N dash, if T is linear and such that it is 1, 1 and on 2, right? And also you have norm of Tx is equal to norm x. Okay. If norm of Tx is norm x for all x in N, okay, you take x in this domain space, small x, okay, and it will be going to T of x, T image of x. T takes small x to T of x. And you look at the norms. X is in N, so here you have to take the norm of N, okay? And T of x is in N dash, here you have to take the norm on N dash. These norms may be different, but the values of the norms are same, all right? If the values of the norms are same for this function T, right? If there exists a linear map T from N to N dash, such that the norm lengths of x and T of x are same, okay? And if this happens for each and every vector x in N, we say the T is isometric isomorphism, right? And T is an isometric isomorphism, and we say N and N dash are isometrically isomorphic, okay? So if there exists a linear map T from N to N dash such that T is bijection, C is bijection, and norm T of x is norm x. He has taken phi instead of T. He has taken phi. You can name anything. Okay. Instead of T, he has taken phi. Phi is okay. Is Greek letter. Okay. So if this linear map is such that norm Tx is norm x for all x coming from the normal linear space N, then T is called an isometric isomorphism. And we say N and N dash are isometrically isomorphic. Okay, so what is happening is this. See, you have an N space here, right? And you have a T space. You have an N dash space. Okay, N dash is a normal space, N is a normal space, and T is mapping N to N dash. Okay, and if this T is linear, and you take any vector here. You take any vector, okay, or you take two vectors, okay, and you let x1, x2 be vectors in N. You look at the distance between them. What is the distance between them? It is the norm of x1 minus x2. Okay, if this is x1 and this is x2, the length between them, or the distance between them rather, is norm of x1 minus x2, where this norm is norm on N. You look at the corresponding images, T of x1, T of x2. Okay. Look at the corresponding images, T of x1, T of x2, right? And look at the distance between them. This is T of x1 and this is T of x2. And you look at the distance between them. That is norm. You take the difference, T of x1 minus T of x2, and take its norm. Okay, that is the distance between these two images. Okay, or vectors. So you take any vector in this normal space n. Look at the T image of that. Okay, and look at its length. These two lengths will be same for any vector. T takes vectors to the same vectors to the vectors. A vector is taken to a vector retaining the length. Okay. So means for any vector, the T image of that vector and that pre-image vector. The T image, this is T image of the vector of the pre-image x. Okay, for x, if you look at T of x, norm x will be same as norm Tx. Okay, norm Tx. In fact, you will be measuring x from the identity. Okay, here you will have the identity. You look at the length. What is norm x? Norm x is the length of x from the origin. Here also you will have origin. You will have the additive identity in n dash. Okay, and you look at the distance. If this is the theta of x, you look at the length. You look at the distance from theta to T of x, from theta dash to T of x. Okay, this is norm T of x. This is norm T of x. This is norm x. Okay, if this is x, this norm x is the distance between theta and x. The A2NT and x. The length of this line, this segment, the distance of A2NT from x will be same as the distance of the corresponding A2NT in n dash and the T image. Okay, these two lengths will be same. Okay, and for each and every vector x, this is true for each and every vector. If your x changes, okay, if this is x1, you will be calculating norm x1. You will be looking at Tx1, and you will be calculating norm Tx1. Norm Tx1. It is this. It is norm Tx1. It is this. Okay, and these two lengths will be same. These two lengths will be same, right? So if you have a T11 and on2, and if T, of course, this is linear. T is linear, and norm lengths are maintained, and T maintains norm lengths. Okay, from n to n dash. Then we say it is these two spaces, normal linear spaces, are isometrically isomorphic. Okay. Next we define isomorphically isomorphic, topologically isomorphic. Next we define topological isomorphism, isomorphism. Isomorphism. Okay, let's define topological isomorphism. The previous one is isometric isomorphism. Now we will define topological isomorphism. Let us again take two normal linear spaces n and n dash. Okay, say you have a linear map T from n to n dash. Let this be linear. Okay, and if your T is continuous. Of course, you also want it to be a bijection, 1, 1, and on2. And if your T is continuous, okay, and if your T inverse, where from T inverse maps? T inverse maps n to n dash to n. T maps n into n dash. In fact, T transforms n into n onto, by two arrows means it is onto n dash. So because this is 1 to 1, you can speak of the inverse function, T inverse from n dash to n. This also will be continuous. Okay, right? So if you have a linear map T from n to n dash, such that this T is a bijection and that T is continuous and T inverse is also continuous, then this T is said to be a topological isomorphism. And we say n and n dash are topologically isomorphic. Okay. In fact, in one theorem, you proved that if T is in 1 to 1 and T inverse is continuous, right? Okay. That's a little different, right? So first, let me define this definition. What happened? Yeah. So let it comma and dash be normal linear spaces, right? Comma T map n to n dash be a bijection, linear, and continuous. Further, if T inverse is also continuous, we say T is a topological isomorphism. Okay, right? And in this case, we call n n dash or topologically isomorphic. Okay, that's what we mean by topological isomorphism, right? If there is a linear map from a normal linear space into another normal linear space, such that the T is a bijection and that T is continuous and the T inverse is continuous, then we say T is a topological isomorphism. And we say n and n dash are topologically isomorphic. Okay, so now we can prove this theorem. Theorem 4.3.5. Theorem 4.3.5. What does this say? Let n and n dash be normal linear spaces. Let n comma n dash be normal linear spaces. Right? Then n and n dash are topologically isomorphic if and only if then n comma n dash are topologically isomorphic and only if there exists a one-to-one linear transformation. There exists a one-to-one linear map, right? T from n to n onto n dash, such and positive real constants. Positive constants have to be real. Real constants m and m, such that m times norm x is less than or equal to norm tx is less than or equal to m norm x. Okay, for all x in n. For all x in n. Yeah. Okay. Here he is not writing brackets. He is simply writing t of x. By this he means t of x. He is right. He is neglecting brackets. He is simply writing tx. Tx means t of x. Okay. Yeah. So let us prove this. Okay. Now, let's prove this part. Let me assume this one and derive this one. Okay. So yeah. So what I'm assuming, this one. Let n comma n dash be topologically isomorphic. Okay. What does this mean? I have to derive this one, that there exists a one-to-one linear map n to n dash and onto, this is a double arrow, onto right? Such that there exists positive constant small m and big M, such that m norm x is less than norm tx is less than big M norm x for all x in n. Okay. Yeah. So let me show this. N and n dash be topologically isomorphic. Let me derive this. Okay. What does this mean? By definition of topological isomorphism, there exists a linear map T from n to n dash such that T is bijection, continuous, and T inverse is also continuous, isn't it? Is also continuous, right? What is the meaning of topological isomorphism? There exists a linear map T from n to n dash such that this T is a bijection 1 and on 2, and T is continuous, and T inverse is also continuous. This is the definition of topological isomorphism. From this, we want to derive this. Okay, what is the meaning that T is continuous? A linear map T is continuous. This is true. For a linear map, continuity is same as boundedness. Bounded linear maps means norm T of x is less than m times norm x for all x in n. There exists a constant big M. Okay, this is equivalent to continuity. Okay, so let us put it in words. Continuity of T implies there exists M positive such that norm T of x is less than or equal to m times norm x for all x coming from big N. Okay. Continuity of T means T is bounded. Continuity of T means linear map. Yeah. T is a bounded linear map. Continuity of T means T is a bounded linear map. T is a bounded linear map. Okay. Continuity of T means it is equal to bounded linear. Okay. From here, you will get there exists a constant m positive as a norm Tx is equal to m times norm x for all x in n. Okay. The domain of T is n. T is a mapping from n to n dash. Okay. So for all. Can I move this? Yeah. Right. For all x coming from n, this is true. Okay. So we have got this inequality. Non Tx is less than m times norm x. How about this? This we proved in one of the theorems. If your T inverse is continuous, this happens. If your T inverse is continuous, you will be applying this on T of x equal to W. Okay, right? So then you will be getting this, right? So T inverse is continuous, right? T is topologically isomorphic. Topologically isomorphic. Isomorphic means what? Isomorphic implies that T inverse is continuous. Okay. This implies that you have this. Okay. There exists a small m positive such that m times norm x is less than or equal to norm dx. Okay. Right. Why? T inverse is positive means T inverse of y, the norm of this is less than or equal to small m into norm y. If your T inverse is like this, if your T is continuous, norm Tx is less than or equal to m times norm x. So if in place of T, if you take T inverse, it will be acting on y. Let it act on y. So norm of T inverse y will be less than or equal to m times, and instead of capital M, I am taking some other constant, small m, less than or equal to y. Okay, where y belongs to n dash. What the domain of T inverse is n. The domain of T inverse is n dash. The domain of T inverse is n dash. Okay, so and T is onto. So if y is in n dash, there will be an x in n such that t of x is y. Okay, so this can be taken as t of x, y. There exists an x in n, right? You are taking y in n dash because for t inverse domain is y, for t inverse domain is n dash. So your y varies in n dash, and t is onto. So for every element here, there will be a previous in n, right? I am taking y in n dash, so there will be an x in n. So t of x is equal to y. Okay. Now you write. What is t inverse of y? If t of x is y, t inverse of y will be x. So this becomes norm x is less than or equal to m times norm. Y is what? T of x. Y is t of x. Okay. And you bring m to this side. So you'll get 1 by m. Okay. You can see that your m can be positive. Your m can be non-zero. Okay. So you bring m to this side, right? You bring the small m to this side. You bring small m to this side. So 1 by m into norm of t inverse of y. T of x is y. So t inverse of y is x. And y is tx. Y is tx. Y is equal to tx. That's how you get this. You get this. Norm. Right. That's how your m times norm x is the norm tx. Okay. Instead of small m, instead of 1 by m, you are taking m. That's the only difference. Okay. And you could have taken right. There exists an m positive in place of right in place of small 1 by m. Had you taken here, you took m. That's why you got 1 by m. Had you taken 1 by m here, you got m here. Okay. So anyhow, it is a positive constant. This is a positive constant. Okay. So that's how there exists a small m positive. There exists an m positive, so that m times norm x, a constant times norm x is less than or equal to norm dx. Okay. This is true for all x and y. Because this is true for all y in n dash, and because your function is onto, as your y varies throughout n dash, your x will be varying throughout n. Okay, that's how here x can be anything. So this becomes for all x in n. Okay, so this is one way, is an upper bound on norm tx, and this is a lower bound on norm tx. Okay, so that's how this upper bound is obtained, and this lower bound is also obtained. So if you assume this, you can obtain this. And let us look at the converse. Okay, so if you assume this one, so then what this inequality means? Norm tx is less than m times norm x for all x in n, means your linear map T is bounded, means your T is continuous. This we proved in the first theorem of this chapter. If your T is bounded, then your T becomes continuous. Okay. Similarly, this means your T inverse is bounded. So it gives your T inverse is continuous. Okay. So let's prove this part. Let m comma small m greater than 0 be constraints such that small m norm x is it norm x or norm dx? Norm dx, right? Small m, no, norm x, I'm sorry, norm x. T inverse of y is norm x. Okay. So norm x is less than norm tx is less than or equal to big M norm x for all x in n. Okay. Let us assume this. Let us obtain that T is topologically isomorphism. Okay. Now this can be split into two parts. Then let us take this part. So this implies norm T of x is less than or equal to m times norm x for all x in n. Okay. And we assume our T is linear, right? Yeah. Our T is a linear map and surjection. Our T is linear in surjection. So right. This implies that T is bounded linear. Okay. This is boundedness. So boundedness for linear maps, boundedness is same as right. The boundedness we are saying is equivalent to continuity. So T is continuous. on N. Okay. Now let's look at this part. Let us take T of x equal to 1. Let T of x be equal to y. So then what happens? If you call this inequality 1, so 1 implies that m times norm x can be written as T inverse y is less than or equal to norm of T of x is 1. Okay. This means, right? This means norm T inverse y is less than or equal to 1 by m times norm y. Here you may see that your m can be non-zero. If your m is 0, you are assuming your m is positive. Okay. So that's why you can bring it to this side. Okay. Now, norm of T inverse y is less than or equal to constant, a positive constant times norm y. This means, right, this is true for all y coming from n dash. Okay. If your x varies in n, your y will be varying in n dash. Okay. Therefore, this means your T inverse A is bounded. And in fact, you can also show that, right? Yeah. So your T, this implies, yeah, because your T is linear, and if your T, right, T inverse is, your T is linear and T is a bijection. Therefore, your T inverse also will be linear. Okay. So T is linear and implies T inverse is linear. This we proved in one of the theorems. You can prove that T, this is, I proved this as an SAQ. So if your T is linear, then T inverse becomes linear, and this inequality gives, if you call this 2, this and 2 imply that T inverse is bounded linear. Bounded linear. Once it is bounded linear, it becomes continuous. Because linear map, if it is bounded, this boundedness, then it becomes continuous. Therefore, T inverse is continuous linear. Okay, so we could obtain that T is continuous linear. We could obtain that T is yeah. Oh, I have to move this. Okay. Yeah. No, this side. No, what? Yeah. Here we showed the T inverse is continuous. Where we showed the T is continuous. No. I'm assuming this part. I want to show T is continuous and T inverse is continuous. Okay. Okay. This I am proving. So this I have. So T is bounded linear. Therefore, T is continuous. This part. This part. Okay. Yeah. This part. Okay. This one. Right. So T is continuous. I assumed these two constants exist. Then I could prove that T is continuous, and also T inverse is continuous. From here we get that T inverse is continuous. Therefore, right? T is isometric. Therefore, T is topological isomorphism. T is topological isomorphism. Right? Hence from n to n dash. Therefore, n and n dash are topologically isomorphic. Topologically isomorphic. Okay, that's how you can prove that theorem. Okay, so yeah, if you assume that n and n dash are topologically isomorphic, this kind of constants exist, small n and small x satisfying this, and that this T is 1, 1 and on to from n to n dash, and also it is linear. And conversely, if this happens, if this thing happens, then you can show that these two are topological isomorphic by showing that T and T inverse are continuous. Okay, so that completes that theorem. Let's look at the next theorem, that is 4.3.6. Any two n-dimensional normal linear spaces or the same scalar field are topological isomorphic. Any two n-dimensional, this is 2, any two n-dimensional normal linear spaces. Normal linear spaces or the same scalar field over the same scalar field or topologically isomorphic isomorphic. Okay, so any two n-dimensional normal linear spaces are topologically isomorphic. Yeah, how can we do this? Let's see. Okay, what we do is let us take let us take two n-dimensional normal linear spaces. Let n comma n dash be n-dimensional normal linear spaces. Okay, we'll show that these two normal linear spaces are topologically isomorphic. Means we have to show that there exists a linear map from n to n dash, which is 1, 1 and 1, 2, and which is continuous, and inverse is also continuous. That's what we have to show. Okay. What we do is, it is enough. It suffices. It suffices to show that n comma fn are topologically isomorphic. Right? In order to show n and n dash are topologically isomorphic, okay, what we do is we'll show that fn and n, these two are topologically isomorphic. Okay, if we can show that these two are topologically isomorphic, okay, from this you can show that these two are topologically isomorphic. This we do for any n-dimensional space n. Okay, if we can show that these two are topologically isomorphic, then instead of n we can take n dash. So then this will be topologically isomorphic to n dash, right? And then you take inverse of this and compose it. Okay, composition of linear maps will be linear map, and composition of continuous functions will be continuous. So that's how these two will be topologically isomorphic. Okay, so it is enough to show that n-dimensional scalar field Fn is topologically isomorphic to n. Okay, so that's what this means. Okay, now we show that these two are topologically isomorphic. So let us start. Yeah. So let us show that Fn comma n are topologically isomorphic. Okay, this will show. So to show this, we define a linear map. We have to show a linear map from Fn to n, which is 1, 1 on 2 and continuous, and inverse is continuous. Okay, so we consider this function. Define. We are saying a capital N is n-dimensional, so it will have a basis. Okay, so let us take a basis for n. Let x1, x2, x3 up to xn be a basis for n. We have assumed that capital N is n-dimensional. So there exists a basis consisting of n linearly independent vectors. Okay, these are n vectors. So I'm taking this as a basis for n. Begin. Okay. Now we'll define a linear map from T to from Fn to n. Okay. Define T from n Fn to n. Okay. What does it do? it takes Fn means what? F cross F cross F cross F taken Fn times. So you will have some alpha 1, alpha 2, alpha 3 up to some alpha n. This consists of n tuples. If it is F2, it is an ordered pair. If it is F3, it is an ordered triple. If it is F4, it is an ordered quartet. And if it is Fn, it will consist of n coordinates coming from each alpha I comes from field F. Okay, this is taken to here you have this basis. So we'll be multiplying vector xi by scalar alpha I. So we'll form sigma alpha I xi. We'll multiply. So these are n linearly independent vectors. These are n scalars. We will multiply xith vector by alpha ith scalar. Okay, we are multiplying xi vector by alpha I scalar. This is a scalar product. Okay, right? Xi's are elements in n. These are vectors in n. These are coming from field. These are scalar products. Scalar product is closed on n. So these belong to n. And these are n vectors. Alpha 1 x1, alpha 2 x2, alpha 3 x3 like that. They are all added. And n is closed under addition, vector addition. Therefore, this is an element in this. Okay. So this is well defined. We have to show that this T is a linear map. Claim. In your book, this is not done. Okay. Because it is easy. In the exam, you have to show T is linear. T is linear. Okay. How to show? You consider T of two. You take two vectors. Let me call this alpha bar. Okay, this is not the bar in the complex space, complex plane. That's just a symbol for this n tuple. Okay, so let me take. Yeah, let beta. Let beta bar be equal to beta 1, beta 2 up to beta n. Let me take this n tuple as beta bar. Okay, let this belong to Fn. Right? This is alpha bar, this is beta bar. Okay, let us consider T of alpha bar plus beta bar. Okay, what is this? You add these two vectors. This is n tuple, this is n tuple. You add them. What do you get? Alpha 1, alpha 2 up to alpha n. This is alpha bar plus beta bar is what? Beta 1, beta 2 up to beta n. Okay. And then how to add these n tuples? You add the corresponding coordinates. This is alpha 1 plus beta 1, comma, alpha 2 plus beta 2, comma, alpha n plus beta n. Okay. Right. Now, what this means? What this means? What this means? This is equal to, right? How is it defined? Alpha bar is taken to this. So this is right. You multiply ith coordinate by xi and add. So this is sigma alpha I plus beta I into xi. The ith coordinate of this must be multiplied by xi. So the ith coordinate is alpha I plus beta I. That should be multiplied by xi and all should be added. Okay. Now this is xi is a vector in n and these are scalars. And we know this scalar multiplication distributes for this addition. And we know this is equal to alpha I xi plus beta I xi. This is from the definition of vector space. Since n is a vector space, this happens. Now, this is sigma of this plus sigma of this because n is a abelian group. N is an abelian group. So this can be written as sigma alpha I xi plus sigma beta I xi. Okay? Because n is commutative group, you can write like this. This is what this is. What is sigma of alpha xi? Alpha xi. This is T of alpha bar. Okay? And what is sigma beta xi? This is T of beta bar. Okay? What is T of beta bar? Sigma beta xi. So if you replace this by beta I, you'll get this as T of beta bar. Okay? And we started with T of alpha bar plus beta bar, and it is equal to T of alpha bar plus T of beta bar. This is one part of linearity. What is the other part? You consider P of a scalar D times alpha bar. Okay. This is T of, you are multiplying alpha bar, means alpha 1, alpha 2 up to alpha n by D, a scalar D, for D coming from field. Okay. This is scalar product. Scalar product. I'm multiplying vector alpha bar by D. So what is alpha bar? It is this n tuple. It is multiplied by D. What is this product? It is you multiply each coordinate by D. That is D alpha 1, comma D alpha 2, comma D alpha n. Right? How to multiply this? How to perform this scalar multiplication? Multiply each coordinate by D. So it is D alpha 1, D alpha 2 up to D alpha n. Okay. And T acts on this. How do you define this? It is sigma. You take ith coordinate here. What is it? D alpha I. Ith coordinate is D alpha I. This is first coordinate. This is second coordinate. Ith coordinate will be D alpha I. Multiply this by xi. Okay. And then I varies. Okay. Now this is a scalar. This is a scalar. And this can be written as what? D times alpha I xi for I. Right? This is again from the definition of vector space. This D can be taken out. D into alpha xi. Okay. And this D is independent of I. So this can be written as D times sigma alpha I xi. This D is independent of I. So this can be taken out. D times sigma alpha I xi. This is D times. What is sigma I? Sigma alpha I xi. This is T of alpha bar. So this is T of alpha bar. Okay. This is true for all D in F. Okay. And alpha bar coming, alpha bar belonging to N. Where? This one. Comma alpha for all alpha bar belonging to N. Okay. So, previously we showed T of alpha bar plus beta bar is equal to T of alpha bar plus T of beta bar. Okay. This property along with this property means that your T is a linear map. Therefore, T from Fn to N is linear. This we prove. Okay. Now we have to prove that it is 1, 1 and not 2. Right? We could prove that T is linear. And next we have to show that it is bisection. Next we have to show that it is continuous and inverse is also continuous. That's what we have to show. Okay. So now let us claim that T is a bisection. T is bisection. Okay. Yeah. Where from T is mapping? It takes Fn to N. How? It takes alpha bar equal to alpha 1 to alpha n to sigma alpha I xi. Okay. To show T is 1, 1. So you assume let it is enough to show T of 0 equal to 0. Okay. Yeah. You assume T of x equal to 0, and if this implies x equal to 0, you have to show that the kernel, the null space is singleton 0. Then your T becomes 1 to 1. Okay, that is one way. Or still easily from the basic definition of 1 to 1s. What do you mean by 1 to 1s? You assume the images are same. Images, let T of x1 be, or T of alpha bar be equal to T of beta bar. Okay. We assume T of alpha bar be equal to T of beta bar. Right? We should obtain alpha bar equal to beta bar to show 1, 1s. Okay. You assume images are same. This means what? Sigma alpha I xi. I am taking alpha bar is alpha I. Right? It's n tuple. And beta bar is beta 1 up to beta n. Okay. So this I'll get sigma beta on xi. Okay. Now you bring this to the other side. The sigma alpha I xi minus sigma beta I xi is equal to 0. So this can be written as sigma. You can take xi common. This is alpha I minus beta I into xi. Okay, because alpha I, beta I are scalars and xi's are vectors, and this is the right coming from a very normal linear space. You can write like this. Now this means what? Your xi's are linearly independent, and these are scalars. This is a linear combination. This linear combination equal to 0. So each coefficient, each scalar must be 0. This implies alpha I minus beta I is equal to 0 for all I. Since beta since xi's are linearly independent. Since xi are linearly independent for all I equal to 1 to n. Okay? These are n linearly independent vectors. They are coming from basis. They are linearly independent. Therefore, these coefficients must be 0. This implies alpha I equal to beta I for all I. Okay? So means what? Your alpha bar equal to beta bar. Okay? You assume that the T images are same for alpha bar and beta bar, and you are able to obtain that alpha bar equal to beta bar. Therefore, T is 1 to 1. For your T is an injective map. It is a 1-to-1 map. Let us show that it is onto. Means we have to take an element here. Right? Now I want to show that it is onto. Let T is onto. So let you take an element W in N. Let W belong to N. Okay? And for N, X's form a basis. So there exists gamma 1 up to gamma N such that W is equal to sigma gamma I xi, where I equal to 1 to N. Okay? Let W be an element from N. I'm taking an element W in N. Okay? I want to show T is onto. So I should be able to get a pre-image X alpha bar in Fn such that alpha bar is taken to W by T. Okay? So W is in N, and for N, Xi's form a basis. Therefore, W can be written as a linear combination of Xi's. I'm assuming these are coefficients, corresponding coefficients. Okay? So what happens? W is this. Now, now what can I say? Yeah, from here you can guess. If alpha bar is alpha up to alpha n, then its image is sigma alpha xi. These coordinates are becoming coefficients of xi's. So because these coefficients are gamma I, you look at gamma 1 up to gamma n, the interval formed by gamma 1 up to gamma n. Okay, so yeah, let me put it. Yeah, so now gamma bar is equal to gamma 1 is equal to gamma 1, gamma 2 up to gamma n, right? These gamma i's are coming from field. These are scalars. They are coming from field. Okay, so this will be in Fn. These gamma is gamma n. These n values are coming from field. So F cross F n times. So it comes from this n tuple comes from Fn. Okay. Now and what is T of gamma? T of gamma bar is equal to T of gamma 1 up to gamma n. What is this equal to? It is sigma gamma I xi. It is equal to W. Right? Sigma gamma I xi is W. Okay. So if you take the T image of for this gamma bar, if you take the T image, it is T of this, and this is defined as sigma gamma I, each multiply ith coordinate by xi. Okay, and this has been equal to W. Okay, so you started with a W in N, and you're able to obtain a pre-image gamma bar in Fn such that T of gamma bar equal to W. Right? You started with a W in N dash. Here you are able to obtain a gamma bar in N such that this gamma bar is taken to W. Therefore, your T is onto. Thus, your T is a bijection. Okay. Now, it remains to show that T is continuous and T inverse is continuous. Well, how did we define T? It is taking n to n dash, and it is taking alpha bar equal to alpha 1 up to alpha n to sigma alpha I x. Okay? Yeah. Now let us obtain continuity. T is continuous. T is continuous. Okay. So how to show? We'll try to obtain this one. Norm Tx is less than or equal to m times norm x. This is what we try to obtain. So let us take the norm of this. Norm of T of alpha bar. Norm T of alpha bar. Okay. This is norm. What is alpha bar? Alpha 1 to alpha n. Okay. What is right? What is this? Norm of what is T of alpha bar? It is sigma alpha x. Sigma alpha x. Okay. And because norm satisfies the triangle inequality, so this and these are scalars and these are vectors. So this will be less than or equal to sigma mod alpha I norm xi. Okay. Yeah. Now, right? Now I will take right. I'll take the maximum of all these. See, now the norm of T alpha bar is less than or equal to this. The norm of T alpha bar is less than or equal to what is this? Sigma mod alpha I xi. Sigma mod alpha I norm xi or I. See, you should be careful. Xi is vector, then you should have norm. Alpha is a scalars, you should have modulus, because if a norm satisfies alpha times a vector is equal to mod alpha norm x. This I used. Norm of alpha times x. For this scalar product, norm is mod alpha times norm x. That I used. Okay. So alpha is must be in modulus. For xi, you have to take norm. And then I use the triangle inequality. You should be careful when you use these symbols. Okay. Now you take the maximum of all this. Let m be equal to maximum of norm xi or I. There are n vectors, x1, x2 up to xn. You take their norms. Right? Let I vary from 1 to n. Okay. These are n values. You can take the maximum of them. Call it m. Okay. Now each norm xi will be less than or equal to this. This is greater than or equal to norm xi for all I equal to 1 to n. Because I'm taking this as the maximum of norm xi's, and each of these will be greater than or equal to the individual values norm xi. Okay, this is n. So because of this can be written as norm T alpha bar is less than or equal to m sigma. This is sigma mod alpha I. Each norm xi is less than or equal to this m. Okay. M is independent of I. You can take it out. This is m times sigma mod alpha I, where I equal to 1 to n. Okay. And I equal to 1 to n. And this is a norm. This is right. Alpha bar is coming from n. Is coming from Fn. Okay. Alpha bar is coming from Fn. And on Fn, this is a norm. This is modulus norm. Okay. So you can write on Fn, this is a norm. This is m times norm alpha bar. Okay. This whole thing is norm. Sigma mod alpha is norm. Okay. So norm T alpha bar is less than or equal to m times norm alpha. Therefore, norm T of alpha bar is less than or equal to m times norm alpha bar. Okay. Therefore, T is continuous on Fn. Okay. And it remains to show that T inverse is continuous. Did he prove that? The book, is it true? Yeah. He is proving that also. Okay. Yeah. He's proved it differently. He's proved a bit differently. I'm proving a bit differently. Okay. Yeah. Now consider this. Norm of T alpha is greater than or equal to M. Right. Okay. Now, right, I proved T is continuous. Then now let us prove that T inverse is continuous. T inverse is continuous. T inverse is mapping what to what? T inverse maps N into Fn. Okay. Right. Now, yeah, T is taking Fn to N. How? It is taking alpha bar to sigma alpha xi. Okay. T inverse brings a y, a w here to gamma bar. Okay. If w is sigma, right? Gamma I xi, then T inverse maps w to gamma bar. Okay. Now, yeah. Now you consider this a small m equal to consider small m equal to infimum of norm T alpha one moment. Okay. Norm T alpha is greater than or equal to M. Norm T alpha. Why? How? No. Can I show how to show this? T inverse is bounded. Okay. T inverse. We now prove that T inverse are bounded. Okay. We now prove that T inverse is bounded. That is to prove that T of alpha is greater than M times norm alpha. Okay. Let A be equal to x belong to Fn, so the norm alpha is 1. Right. Then it follows that A is compact and closed. Okay. Yeah. Let me consider this. He says, right. Not this. He says to consider. We want to obtain this. We want to obtain norm T alpha is greater than or equal to small m times norm alpha. Okay. For all alpha. For all alpha belonging to Fn. Okay. Rather alpha bar, you may use alpha bar. In your book, it is used alpha. Okay. Now, he is telling to consider x in Fn such that alpha norm alpha is equal to 1. It is an alpha in Fn. Now, consider A equal to alpha belonging to Fn such that norm alpha equal to 1. Okay. This is the unit sphere. This is the unit sphere in N, right? Alpha, right? This is unit sphere in Fn. In Fn, alpha is coming from Fn. This is unit sphere. Their lengths are ones. So this is unit sphere. Okay. Now you let small m be equal to infimum. Small m be equal to infimum of norm T alpha, such that alpha belongs to A. Yeah. Right. For when alpha varies in this unit sphere, you consider norm T alpha. Okay. Now, what happens? Will this be positive? He says M is positive. A is closed. Since A is closed, why A is closed? A is closed. A is closed. Why? Because norm is continuous function. Norm is continuous function. This is inverse image of. Right. This is T inverse of singleton 1. Okay. This is inverse image of 1 and T is continuous. So this will be closed. Okay. This is closed. This is a closure set. Right. Yeah. Now, because this is closed, he says M is positive. Since A is closed, M is positive. Why? Why? Right? The infimum is a kind of limit. Infimum is a kind of limit. And this is continuous function. Okay? Limit of a continuous function. Therefore, and this is closed. Therefore, it has to belong to, this value has to belong to, right? Right? So if you look at the inverse value, alpha, it will be here. Okay, this will be attained. This will be attained in this. Okay, because it is closed. Because it is closed, the inverse image of this will be attained in this, and these are non-zero vectors. Alphas are non-zero because of this. Because the length is non-zero, these are non-zero vectors. That is why, because M is attained in for one value, for one point in A, so M will be positive. Because this happens because your A is closed. Okay. Now from here, what can you write? From here, what can you write? This means what? Norm, this implies that norm T alpha is greater than or equal to small m. Is it correct? No. Right. Now, what this means? Yeah, what is m? M is infimum. So it is infimum of all these individual values. If you take individual value, that will be larger than infimum. If you take individual value, that will be larger than m. It is like this. If you take infimum of 1 by n, if you take the infimum of 1 by n, infimum is 0. And 1 by n is, each 1 by n is greater than 0. Each 1 by n is greater than 0. Okay? So that's how it is happening. So infimum value is less than each of the individual values. That's what is written here. Okay? Now, you consider this for beta not equal to 0. For beta not equal to 0, for beta not equal to 0, you consider beta in Fm or beta bar you take in Fn. Okay, and you form alpha bar equal to beta bar by norm beta bar. Okay, so then norm alpha bar will be 1. Then norm alpha bar will be 1. Right? Norm of this by norm of this. I'm assuming beta bar is non-zero. Means at least one coordinate is non-zero. So norm of alpha bar will be 1. Now, what do we have? We have that norm of T alpha, that is T of beta bar by norm beta bar is greater than or equal to small m. Okay. Norm of T alpha is greater than or equal to m. So in place of alpha, I am taking beta bar by norm beta bar because this is in A. Okay. Right? For alpha in A, this is true for alpha in A. Okay. This is true for alpha in A. Now, norm T alpha is greater than or equal to m. So this is in A because norm of this is 1. So norm of T alpha is greater than or equal to m. This can be taken out. This is norm T of beta bar by norm beta bar is greater than or equal to m. Now, this can be brought this side, right? T of b bar. So norm beta, right? M times norm beta bar is less than or equal to norm T beta bar. Okay. So this means that your T inverse. This means that your T inverse is continuous. Okay. So that's how we could prove that T is continuous and T inverse is continuous. From here you obtain this, right? This is lower bound of norm T bar. Okay. This is upper bound. Right. This is upper bound. This is upper bound in terms of norm alpha bar, and this is upper bound on T of alpha bar. This is lower bound. This is lower bound on T beta bar. Okay. Therefore, your T inverse will be continuous. So we proved that T is continuous, T inverse is continuous. Thus T is continuous and T inverse is continuous and T is linear bijection. Okay. Therefore bijection. Therefore Fn, N are topologically isomorphic. Okay. So that's how. So once you prove this, any two finite dimensional normal linear space of the same size will be topologically isomorphic. Okay. So that's how we prove this theorem, right? That's how we prove this theorem. That any two n-dimensional normal linear spaces or the same scalar field are topologically isomorphic. Okay. So with that, I stop today. Right. In the next class,
1 minute, sir.
yes, yes.
Last line, T inverse is continuous, then?
Yes, yes, yes. Which one?
Last in the end, sir. T inverse is continuous.
Yeah. T inverse is continuous. T is linear bisection. So T is continuous, T inverse is continuous, and T is linear bisection. Therefore, Fn comma n are topologically isomorphic. Okay? Okay, sir. All we proved. So from here, it follows that any two n-dimensional linear space, normal linear space of the same size, of the same dimension will be topologically isomorphic. Okay? So with that, I stop today, and tomorrow I'll continue with the equivalence of norms, and I'll try to finish this chapter tomorrow. Okay? Right.
Thanks, sir.
Any questions?
Thank you, sir. Thank you, sir.
So, okay. Thank you very much.
Thank you, sir. Mm-hmm.